All right, we're gonna restart that intro. Curtis, once again, nice to meet y'all. This is Julius, and yeah, welcome back. So this workshop is going to be two parts. The first half is going to cover optimizations, various cost functions, just stuff like that. And then the second part, we're going to get into convolutional neural networks, and then we're going to have a live coding example, so you guys can finally. We touched upon PyTorch, but I'd like you guys to actually start coding a little bit in this workshop. So yeah.
Before that, we announced on our email list applications for eBoards. So if you want to become part of this and want to organize events in the future, not necessarily this course, but we do a lot of other things, check that out. And if you're attending this course, obviously, then you have a pretty high chance of getting in. So, yeah. And also note that attendance is on Piazza as usual. Just check in whenever you have time. It's open for 2 hours. So, yeah. I guess we'll get started. So first of all, in deep learning, we just need a lot of things to go right in order to make it work. So there's a lot of tricks. For one, there's the data. So you could have all sorts of data. Like data could be so messy in industry, for example. You just have spreadsheets of data. You could have data that has missing labels or that's just unavailable at some points. And so you have to way of dealing with those types of things. But for this workshop, we're not going to deal with that because that's more of a data scientist type of role. So we're going to assume our data is kind of clean in this one. But second one is our model. A model essentially was what deep learning model will use, or not necessarily even a deep learning model. It could be regular machine learning model, or yeah. And so in a deep learning model specifically, you would determine what layer there are activation functions and your loss function, and those are all different types of things you have to design in order to make your model work the best. And that's usually just the process of iteratively experimenting on your data. And there's not really a correct term to do, correct set of models that you can use, but depends on the type of problem and mostly your data as well. Yeah, and specific thing we're going to mention later is weight initialization. It's just we've learned so far that how a deep learning neural network works, but we haven't talked about how the weights are initialized and then how that learns. So we'll talk about that. Hyperparameters. These are basically such as your learning rate, batch size, and many other things. You could have many hyperparameters for your layers, what kinds of layers, what types of activations, and inside your equations, what are the parameters that multiply against this parameter. Some things that you specify ahead of time before you start training the model. And your optimization algorithm, this usually involves some type of gradient descent. So there's stochastic gradient descent and batch gradient descent. Just by the first term, you can kind of guess how it works. Is stochastic meaning it's one single example at a time, and it just stochastically gets to the optimal value. While batch gradient descent, you have you analyze all of the data at the same time and then go in a directly fine-tuned approach. So, and then you have momentum, Armis-Prop, and atom optimization. There's more advanced methods in optimizing your weights. And basically, we have momentum, Armis-Prop. These are two different methods, and then atom is basically the combination of these two previous ones. And then we have regularization, which is basically how to prevent your model from overfitting, basically memorizing the training set and then doing so poorly on the test set. So, and here's some methods to prevent that. So yeah. any method that prevents overfitting is called regularization. Yep. So, right. Do you want to explain this,
Honestly,
Okay.
I'm gonna just sit down and come back the second half.
or? Okay. Okay.
I feel awkward just saying.
So yeah, vanishing and exploding gradients. So this is a common occurrence in neural networks. Basically, during a backpropagation when the gradient is calculated. So, for example, we have a gradient of this sigmoid function. So the solid curve is the sigmoid, the dotted curve is the gradient. And as you can see, there's a small derivative at the end points here. And the problem with that is when you multiply your weights by the chain rule, basically it's going to be a long product of terms. And so when you use the gradient to update your weights by a certain amount, that certain amount is going to be very small. And so as you can see, like the limit of 0.5 to the x is 0, because anything less than 1 and above 0, when you multiply it over itself again and again, it's going to be equal to 0. And then same goes for anything that's above 1. If you do it multiple times, it's going to go to infinity and blow up. So you got to be careful what your gradients are. So yeah, if your network is very deep, then this can lead to exponentially collapsing to 0 or infinity. And then your model just like blows up in terms of the weights, or just stalls and does nothing. So how do we fix this? Well, one is we could use the ReLU function. So this is a different type of activation function where it's just the max of 0 and the value. So basically, anything below 0 has a derivative of exactly 0, and then anything above has a derivative of 1. And so the reason why we do this is so that if we want to discard any features that we don't think is important, it has a activation of 0. So that way, as your neural network learns what features are not important, it will set the gradient to 0. It'll keep going down until it hits some point here. But otherwise, the gradient will be 1, so that we can freely move up and down this curve here at the same speed, basically. And also, you could have good weight initialization. Basically, as before here, you basically just set your weights so that they're all within this range initially. So that way you never start out with very high gradients and then your model doesn't learn. Okay, so that's that. So how do exactly we do weight initialization? So how do we do that? So there's many ways. Well, we could just start it to an arbitrary number or set it randomly. Usually we make it random. But we do want to make the initialized weight as close to the final weight as possible. So think of it as, in one shot, you set your network equal to what you think is right. Obviously, that would be pretty hard, but we can do a distributional analysis on the weights and basically say, we think that the model distribution would be tended towards this thing. So we basically sample randomly from some distribution of weights, and so that distribution will likely be close to the final distribution of weights in terms of probability speaking. Yeah, so let me just check here. Okay. All right, so yeah, we talked about how we want to set the weights close to as the distribution as possible. And so here's one thing our initial guess is we just set everything at 0 because it's not too negative, it's not too positive. Features will either learn to go in the positive direction or go in the negative direction, right? So the problem with that is that we have this symmetric weights problem. So basically, when you take the derivative and all of the weights are 0, that means that our derivative will be the same for every single weight. And so basically, at that point, you're learning a function with one parameter instead of a whole weight matrix. So instead, we could just make it close to 0, but a small amount of weights, a small amount of randomness. And so it would be like 0.01 times a random uniform distribution, right? This will fix the symmetric weight issue, but we still don't know how the parameter should be, or how close to 0 the parameter should be. Like, should we set it like super close to 0, or should we set it very far away? So what we do is we do Xavier initialization, and basically it's this. So we have a uniform distribution that we want to set it to, and we have our uniform distribution from negative variance to positive variance, and we define our variance to be equal to this. So in a recent paper, or not recent, but like in a paper in about 2010-ish, Yoshua Bengio, a guy that got the Turing Award recently, basically published a paper with this guy called Xavier, and through mathematical proof, they deduced that the optimal distribution of weights should be this. Since it's hard to get into the details without going into tons of derivations, I'm going to keep it at this. You can look at it yourself if you want to. But essentially, all you need to remember is that it's this kind of formula. You don't even need to remember the formula because in deep learning libraries, they already implement that, and that's become the standard. So you're good. You don't need to worry, essentially. So yeah, and then we're going to move on to other types of things, tricks, I guess. So we have this problem of overfitting and regularization. So they essentially mean the same thing. We got to prevent these kinds of extreme weights. Yeah? Oh, yeah. This, yes. Yeah. I don't know why it's not going there.
Yeah. That's okay.
All right. What's going on? Maybe I'll just wait for a while. Okay, so basically, the problem with overfitting is this. So you have an underfitted graph here because you have just fit a straight line and it's not like supposed to be curvy like that. This is a generally well-fitted line, something that fits the data well. And then this is overfitted, where you just have a line going through every single point. But usually we want our model to predict something like this. And there's a way to do that, say if we penalize very high weights. So that way we can't have these like very steep slopes that curve around everything. And if we penalize high weights, that way, so it will learn something like this, but we don't want to penalize it too heavy so that they're 0 and then like they turn into a straight line at some points. So that's the point of L2 regularization. Basically, we add this term to the cost function. So we take all of the weights, square them, and add them. So basically, if they're high in value, then you would have a large penalty to your cost function. So when you optimize your model, it optimizes for smaller weights. because when you take the derivative with respect to this, then you get the value of change that decreases the weight, basically. Any questions? All right. So yeah, this basically minimizes the complexity of the model. Yep.
So what about the cost function? You put that through the cost function and then
So say you had cross entropy cost function, you would just do plus this, essentially. So you have the formula for your cost function, and then or loss function, you add the weights, basically. So, or do you want me to explain like the intuition behind it again? Or? Yeah, so basically by adding this term, you would have the cost function on one side that if you do gradient descent, it would optimize for that term. So it's optimizing for having a lower error on the model, right? But on the other side, if you're optimizing for lower weights, then it will do that as well at the same time. So you're basically balancing out these two optimization problems of reducing the weights and reducing the error in the model.
So from a math perspective, just to remember, we're taking the derivative of our cost with respect to the actual weight. So if we take the derivative of that by Wi or W0, it's just going to be 2 times W0, and then we just add that onto the actual cost. So because we're trying to penalize having larger weights, that is going to give you a larger error the larger the weight is, if that makes sense. That's why we're adding it onto.
So essentially, it just takes this thing and moves it to the left. All right, so we're going to go into some commonly used optimization algorithms. So this is the basic one, stochastic gradient descent. Basically, I think you'll benefit from not looking at the slides. You can read over this later, but just try to think on my explanation. So as we said before, basically you want to get to the midpoint over there, but essentially in stochastic gradient descent, you're taking a single data point, computing the error of direction of error that you need to decrease, and then you take a step in that direction. But it turns out for the single data point, it says the error is this way, but the actual point is over there. So you take another sample, and then you say, where's the error for that sample? Well, it turns out it's this way. And then you go that way. And then basically, you do that for every single data point, and then you would go like this, zigzag around, and then you finally get to a single point where the lowest error occurs, right? So the problem with that, or there's pros and cons with that. Pros is that it can explore a large cost function area. Cons of that is that it's not necessarily direct and might veer off course. And there's some other cons where you can't do parallel optimizations. You have to do it strictly sequentially. So yeah. And then, oh yeah, here's a visualization of that, basically. So regular gradient descent, you would just go straight towards the local optimum, while stochastic gradient descent, you would just, for each point, calculate the error and then go in the direction that it generally thinks that is the lowest point. All right. And then on the contrast, we have mini batch gradient descent. So basically, it's similar to stochastic gradient descent in that it takes, instead of one single example, it takes a subset of examples. So you basically compute the error for one direction, another direction, and then you add it up, and then it turns out to be in the direction you want. So that way it's kind of an average over some multiple examples. And so as you can see, that's why there is less fluctuation in batch gradient descent, or in mini batch gradient descent, than stochastic gradient descent, which is not here, but stochastic gradient descent would basically have more jagged lines. And then batch gradient descent is essentially when you have the sum of every single example. So that's why batch gradient descent has the lowest, it has the smoothest curve, is because when you take the error of all of the examples and then go in a direction that minimizes the error for all of the examples. So that's why it's smoother in terms of the loss function, because it never increases the loss at any point. It never increases the error at any point. Does that make sense? All right. So here's a comparison of all those methods. So we have batch gradient descent, mini batch gradient descent, and then stochastic gradient descent. So for the batch size, we basically say at each step we want to take in the error for the whole data set and compute the overall direction that we want to go to. For mini batch, we compute a subset, say powers of 2, just to optimize for their computer architecture. And you take those many examples and then compute the general direction. And then stochastic gradient descent is just one.
When we were first looking at gradient descent, was that stochastic? Or was that some other?
So the example that we saw in the previous workshop is stochastic gradient descent. And also batch gradient descent, but we're technically just defining it now, basically. So when you have like a for loop that iterates over everything, then that's stochastic gradient descent. If it's if you're doing matrix multiplications, then you're doing batch gradient descent, essentially. Yeah. Okay. So then we have updates per epoch. So basically, you have to wait until you compute the error for every single point to do one update. So it's much slower for batch gradient descent, and similarly, it gets faster for every for smaller batch sizes. So this would be a batch size of 1, and since you're updating per sample, it takes a smaller amount of computation time for each calculation of the error, and so you basically make updates faster. And then we have advantage with our GPT, using our GPU for matrix multiplications. So it's higher for batch gradient descent because we're just taking a large matrix and multiplying it, and it gets smaller. We get smaller advantages with smaller batch sizes. But actually, there's a warning here. So if you have really large batch sizes, or say you have a ton of data, like you have millions of examples, sometimes your examples will not fit inside the memory of the GPU. So what you have to do is you have to use mini batch gradient descent to split up your data into chunks, and so that way you can train it. And yeah, so you can speed up your model by some amount by taking the average, but you have a trade-off where you might not have faster updates, or you might not fit into memory. So it's basically batch size is the hyperparameter you want to set before you train your model, and then you just play around with that value until you find like the fastest training time or the most fastest convergence. And yeah, update stability may play into some considerations. So stochastic gradient descent is like used very sparingly most of the time because of this, or sometimes you want to just quickly find out what parts of your cost function looks like. So you use stochastic gradient descent. But for the most part, most people use mini batch gradient descent because it balances the trade-off of these two. All right. so we're going to go into optimizers. So the basic premise of this is that we want to improve gradient descent to go in the right direction faster. So here are a bunch of different algorithms that we're comparing. The fastest one would be atom optimization, and basically atom optimization uses the combination of the previous two, momentum and RMS prop. So we'll go into the first one. So here we have stochastic gradient descent with momentum. Basically, if we have a problem of we have a very steep slope in the vertical direction, so the gradient is very large, or the slope is very large, so you want to make a huge change in that direction, right? So the problem with that is you might have uneven axes, where in this case you want to go really far that way, but then at B you want to go really far to C. So it just oscillates really frequently until it gets to the local optima. One way to solve this is to shrink the amplitude by adding momentum. So the momentum term basically, you can think of it like a ball rolling down a hill. So a ball would gain momentum and then it wouldn't suddenly curve in one direction versus curve in another direction. It would go one direction slowly and then pick up momentum. So basically when you start from point A, it would start gaining momentum in the horizontal direction towards the local optimum. All right, so everybody got the intuitive explanation? Yeah. All right, so to actually implement that, basically what we do is we keep exponential average. So exponential average is basically you take the average of the previous time, or you take the average of the previous time step and then multiply it by some amount and then add the new time step. So it basically, this is the formula for it. So for each weight, you're basically taking multiplication with beta for the previous time step plus 1 minus beta for the current time step. And then we do that similarly for the biases. So here's the weights and biases. And then to update that, we just, instead of doing minus alpha times the derivative of the weights, we do minus alpha times the velocity term here, v. All right, so everybody got that?
So in PyTorch, you guys would just be like the same number for momentum, and this whole, all of these, I guess, formulas get abstracted out.
Yeah, so there's ways in PyTorch to abstract this, and you can just use like one function call, and then your momentum term b or beta would be your hyperparameter that you set beforehand. Okay, ignore all that text, but basically RMS prop is instead of doing this with the momentum, basically what we do is we literally take the landscape and squash it into a circle. So that way, when you're dealing with a circle, you won't have these weird oscillations. So if you focus on the equation below, all right. So let's take a look at. Let's start from the high level and just take a look at this. So what you can see is you have a weight minus alpha times the gradient, right? That's what we had before. But now you have this term. So you're dividing by some term. And basically what this acts as is a normalization. So basically we want this term to say if we have a very large width, then we want to shrink that. If we have a very short thing, we want to multiply it so it gets bigger, right? So to do that, we want to make a circle, right? So why do we take the square root of this? Well, this is going to be basically our weight here, but we take our weight and compute an exponential average of our weight. So if you don't think about this, our S dW basically equals to our dW squared. And so when we take our dW squared, put into S, put into here, we get the square root of the square of that, which turns into just dW. So if you think of it as dW over dW, which is equal to 1, right? So basically, since that's 1, we essentially achieved a circle landscape because we are always updating by a similar amount in each direction. So to add complexity, we just add, or not complexity, but to make it more smooth in our updates, we just add an exponential average so that at one point because the loss function may be hilly or it might have a different shape, we want to average out those kinks in our loss function so we don't have like a sudden change to our update for no reason. All right. So do you guys understand the intuition behind that? Okay, I guess I'll assume you do. Any questions? Like, you can ask me anything, really. All right. And then, so atom optimization, yeah, sorry for this, we just copied from some notes, but basically, we have the formula up here. So from here, you can see that we have two things. We have our velocity term that we had from momentum, and we have our squared error term here. So those are the two things we had before. So remember, in momentum, we had V. In RMS prop, we had S. And then basically we're taking those two things. So instead of the gradient, we're just using the velocity term. Instead of not normalizing it, we add the normalization of the squared error, right? So, and then we have our typical formula right here. And then we label each hyperparameter beta 1 and beta 2 just to distinguish between those because those are different values that we set beforehand. And then, so that's our optimization algorithm. Okay. So yeah, ignore the text as usual. And so basically, we have atom as like a hyperparameter, and you can use it in your abstractions with PyTorch. So it's basically like a single function call. Instead of saying do gradient descent, you just say dot atom in your optimizer, and then you're done basically. So you don't even have to worry about this. So yeah.
All right, what's up, guys? Is everyone alive? I know we just had pizza. It's like late. Everyone wants to go home. It's Wednesday night, trying to do homework. But we're gonna try and get through this because we're running a little low on time. So just picking hyperparameters. So basically, once again, you don't really want to pick weights that are exactly 0 because then you get the same like derivatives with respect to the weights from everything. So you can either do Xavier initialization.
No.
Or
this is hyperparameter. So basically, say we want to decide what the learning rate is. So the learning rate is typically you want to have something small, right? So if you want to be smart about choosing your hyperparameters, then you wouldn't want to just pick values on like a simple scale. You want to pick it on a log scale because a log scale you can see how much smallness you want, I guess. And so if you want to do like a random search, you don't do a uniform random of the learning rate. You want to do something on the log scale. So you could do like something like that. A equals 10 to the negative 4 times random. and then that would give you a random hyperparameter on the log scale.
Wrong side. I just read the title.
Yeah.
All right. So yeah, this is just learning to see. Okay, I'm gonna just breeze through this with you.
Yeah. So learning rate, basically you just turn down the learning rate over time so that you converge on the local optimum. This is useful for stochastic variance, essentially.
All right, computer vision. So we have a big problem in machine learning where we have images. We want to analyze them. You can basically think of an image as just a three-dimensional matrix with a bunch of points. So instead of x-axis, you have r. Instead of y, can be g. Instead of z, it's b. So we want to handling these images is very difficult, and that's where an aspect where machine learning thrives. So some applications of being able to analyze images include object detection, as you can see, drawing rectangles over objects, being able to know what's like in your field of view. This can help with driving cars and whatnot. Path planning, facial detection, a bunch of other stuff. So classifier is basically you just give, let's say, it's just classification problem. So you give a model some image, let's say a person's face, and then it can output a classification, like a name. For example, I can make a model that can distinguish between me and Julius, just based on visual features. So when handling images in code, we're basically going to have a three-dimensional matrix. So we can imagine an image, let's say a 32 by 32 array. So it's just going to be, there's 32 pixels on the x-axis, 32, that's just the dimensions of the image, and it's going to have a depth of 3. That's for RGB values, right? So in traditional, just vanilla neural networks, it's very dense. You guys remember the whole spiderweb looking image? We're basically going to flatten this array, and it would just be 32 times 32 times 3, which should be 3072 unless I did bad math. And then that would just be the amount of neurons you have in a layer. So what, in 2012, a paper called AlexNet basically kind of spawned convolutional networks, which is a way in which instead of having this linear one-dimensional array of 3,000 neurons, we can do something a little different. So we're going to bring an idea of filters. So filters, kernels, however you want to call them, you can think of them as like a sliding window. So here we have a 32 by 32 by 3 image. A filter will just be like a small rectangle that we're going to map onto a part of like an image. So we superimpose the kernel over a section, and then we do element-wise, we just do a dot product. So we're going to multiply every single RGB value by every single value in this kernel, and we get back one number. Okay, so there's filters, it's just this blue box, image, pink box, dot product. You put it in like an area, and then you get one number out. And remember that filters have depth. We're gonna kind of just abstractify that out because it doesn't matter too much for future stuff, but there's depth to these filters. So just an example, let's say we took this blue rectangle and we put it in the top left corner. So in the image, these are the values that are in top left corner. In the kernel, these were the values we actually assigned here. So this, you just do the multiplication. Remember this is depth-wise, but for this example, it's just one layer. So instead of going through RGB, it's just R, just because we're keeping simple because 3D stuff is hard to visualize. So you just take this dot product and you get one number out. So this is an example with different numbers. So when we move this over, we want to choose another hyperparameter called stride. So stride is going to be how much do we jump across the image. So for example, in this lovely visualization, we have a stride of 1. So we have this moving filter that has these values. Once again, there's a depth. The depth is 3, for example, but we're just showing it as a 3 by 3 for now. So we have a stride of 1. It's going to move it across, and you can see we're getting numbers out. And then we get this convolved feature, which we can also call an activation map. Okay. I know I kind of just like sprinted through. Does anyone want me to go back? Show of hands. Who's like okay with what I said thus far? So we got filters. Give me fingers 1 through 5. 5 meaning confident, 1 meaning not. You understand what filter means. You get strides and
What's a stride?
okay. So stride is how much this is like moving. So for example, this is moving one column at a time, right? So if we had a stride of 2, like the top left corner might be here, and then it go here, and then here. But because it's 1, it goes bam, 2, then goes down 1. So that's just like how far it's moving.
And why are there cross one across there?
Yeah, so this is the values of, so this is the filter, right? So there's 9 values. So we're basically doing, let's say it starts here. It's going to be 1 times this 1 plus 1 times this 0 times. Yeah. So the weights is this inside the filter. So you can think of filters as weights, pretty much. And then we're just taking the dot product between the filter and the image itself.
I think I get how it works, but I'm not really sure what
Yeah.
it's doing.
So we do this because this gives us an idea of like spatial awareness in the image. So if we have a one-dimensional vector, it's like the weights are kind of a little bit uncorrelated. But here, the weights inside of these filters are looking for specific things. So what will end up happening is you'll make like activation maps. So here we had one activation map. We've got a stacked one, and each of these are just representing different kind of parts of like the image.
You can change the weights for each map.
Yeah, so each map is generated from a different filter. I'm going to go over that in the slides in a bit. But yeah, it's just like they're grouped together, so it's like spatially aware.
And what's a kernel?
A kernel filter, it's the same word, synonymous. We interchangeable.
Oh.
So the terminology might just be intermixed. Don't get them confused. All right, once again, fingers 1 through 5. Kernels, strides. Everyone good? Okay. Questions? Because like, do you have a question? What are you not confident on?
Well, I mean, I guess I just should be familiar with those concepts.
Okay, yeah. So once again, filter is just this sliding window that has a depth. This is your image. Take a dot product, get a number out, and that gives us a convolved feature. So, so I said before, each of these activation maps, which is just like the output of moving a filter across an entire image, is going to produce one activation map. So in this case, we have 6. So that means we use 6 different filters. So each filter is going to have its own set of weights and biases. And yeah, this will be like an output of a convolutional layer. So if you guys remember, here we have what's the dimension of this image? Someone just shout it out, and I'll give you an intel package. We have some swag here, so raise your hand. Oh, he was first.
It's 5 by 5 by 3.
All right. You can pass this to my man in the back. That's right, Devin? We can just hand these out. All right, cool. Yeah. So yeah, we have a 5 by 5 by 3. But when we get this filter, this activation map is a 3 by 3, so it's shrank, as we can all see. So we want to, when we're making our models, we have to be aware of like what are the dimensions of our data, because then you'll get problems with matrix multiplication. Stuff doesn't add up, and then you cry because it's just annoying having to debug. So one little, formula to figure out the dimensionality is we have n minus f divided by stride plus 1. So what that means is this 5 by 5. So our filter is going to be our f, so it's an f by f, so 3 by 3. The image is an n by n, so 5 by 5. So it would just be like 5 minus 3, which equals 2 divided by 1 plus 1, which is 3. Good math? Everyone okay with that? So basically, this is just how we figure out the dimensions of the activation maps. So some practice problems. So what would be the output size of a 5 by 5 by 3 filter with a 32 by 32 by 3 image with a stride of 1? First person to answer this gets another intel. Ooh, one person. Huh?
28.
28? All right, let's see.
I'll have them. I have 2 already.
Oh, okay. Well, then you should have raised. Okay, all right, it's whatever. Yes, 28. So yeah, once again, 32 minus 5, which is the size of the filter, gives you 27. Divide by 1, 27. And then you add 1 and you get 28. So that's going to be the dimensions of this. This will make sense why we need to know this when you stack more convolutional layers, and we'll hopefully get to that in the code. So if you get a fraction, let's say we want a stride of 2, then we just don't use that stride. Once again, stride is just how much is the filter actually moving across the image. I see confused eyebrows. Are we okay? Fingers 1 through 5. How good is everyone up until this point for the section? 5, 5, 4, 5. All right, cool. Any 2s here, no? All right, nice. So alternatively, so as we notice, this shrank the image. So sometimes when we shrink images, we're kind of losing features and information. So you can shrink an image by having a larger stride because you're dividing by that. So if you have a large number, divide by a larger number, it becomes smaller. If we want to maintain the dimensionality, we can add a thing called padding. So yeah, activation map shrink, yada yada yada. So padding is basically just appending zeros onto like a border of an image. So imagine this is our image, and then this is just like a black line. We pretty much just add that black line around just to fit the dimensions so that when we make the activation map, it's the same dimensions. So in the case before, it was a 32 by 32. If we add a padding of 1, that's going to add a 0 onto each side. So instead of 32 by 32, it becomes a 34 by 34. So if we have a 7 by 7 and we add padding of 1, it becomes a what? 7 by 7 image with a padding. 9 by 9, cool. Participation, I like it. I'm only in the middle. So yeah. So we can use this technique of padding just to maintain the dimensionality so our images don't shrink too much. Alternatively, we might want to actually shrink our information. So if we want to just shrink stuff, then we can just increase the striding, but there's an alternative way of doing it, which involves pooling. So just to recap, we have a convolutional layer, and then it just shrinks as you can see. We're going to get into what pooling means, and you guys remember ReLUs, all of this stuff. So a pooling layer is essentially, before with our filter, we were doing a dot product between the filter and the image, right? So a pooling layer is effectively just using a function and putting all of the image data inside of that filter into that function. So you can kind of think of it as, instead of doing a dot product with this rectangle, it's just a max pooling layer will just take the maximum value. So whatever the brightest color is inside of this region gets mapped here. So we can use this to shrink data in a computationally effective way. So this will allow us to shrink to get lower resolution, and yeah. So yeah, there's max pooling. Once again, it's just applying a max function. So you just take the largest value. Let's say this was the top left corner. We just grab 255 and we append it there. 255 there. Yeah, yada yada yada. We can also use average pooling, which averages it, but in practice we tend to use just max pooling. So max pooling and just increasing strides are two ways to shrink your images. The reason why we use one over the other, so once again, max pooling, it's computationally effective because we're just using a max function, right? So there's no multiplication, addition, all this nonsense. Whereas when you increase stride, it might, because we're using just another filter and going across, it'll be computationally more intensive, but there might be more information we extract through that because we are, once again, doing that whole gradient descent upon those weights and whatnot. Not that we're not on the max, but yeah. So convolutional layer, ReLU, we can add pools just to shrink the stuff, and yeah. We ended off with a fully connected layer, which would basically just take this weird tensor that we get as output from convolutional layers or pools, and extract into classification thing. So the last thing we're going to cover are dropout layers. So dropout layer is basically, who here remembers the overfitting thing from before? Numbers 1 through 5. If 5, 5, 5, 4, 4. Okay. So yeah, a dropout layer is essentially turning off various neurons within our convolutional layer in order to make sure that one neuron isn't just completely dominating the rest. So we'll do that by giving a probability of turning a neuron off, let's say 0.5, and then we effectively multiply each neuron by 0 with a chance of like 0.5. So half of the neurons in each training iteration will be turned off, another half will be on. So let's say a dominant neuron is turned off, that means the weaker neurons have to like have a larger gradient to like, you know, be able to train a little faster. So this can help you if you have like overfitting or whatnot. So yep, and then we normalize by dividing by the probability of p, which basically just lowers the expectation, because if we're only doing calculations on half of the training data at a time, then they're going to have just large weights, which gives us the exploding gradient. So yeah, that's normalization. And when we do the actual classification, we are no longer dropping neurons. So the dropout layer, once again, is only for training. So numbers 1 through 5, one more time. Okay, any questions on the dropouts? Okay, so the normalization part or dropout layers itself? Okay, I got it. Yes. So dropout layers. We're taking each neuron and we're multiplying it by 0.5. There's a probability of whether or not we use a neuron when we're training. So let's say that probability is 1/2. So we just flip a coin. We're effectively turning off half the neurons at every training step. The reason why we do this is because there might be a bully neuron that just has a high gradient, which is telling everyone, okay, I'm really good at what I'm doing. So yeah.
How do you get the probability?
So that's a hyperparameter. We just said it.
Oh.
So a very common one is like 1/2. So yeah, we just want to turn off neurons that are like overwhelming to allow ones that should be working but aren't because someone else is doing their work to get a higher like chance of working because the other value isn't there. So if you do that and then you normalize it, everyone is doing like a fair share. And yeah. So when you have very large gradients, that tends to give you an overfitting problem. So we're trying to avoid that. Fingers again. 1 through 5. All right, cool. So now we're going to get into a coding example. We have 5 minutes left, so if it goes over, you guys once again are free to leave. But I just want you guys to get a little hands-on with PyTorch. So this is going to be a little bit of a recap from the last lecture. So if you guys want to say, get into pairs of 2 and open up Google Colab. So who here has used Colab before? That was 1. Okay, it's fine, it's fine. So Google Colab is just Jupyter Notebook, but in the cloud. So they have a lot of tools for you to use. It's really fast, etc., etc. So I'm gonna make a new Python notebook. And yeah. When everyone has it opened, just like give me a thumbs up or something, so I know I can continue. Yeah, just make a new one. We're just gonna do some scratch. So I don't know how far I'm gonna get into this, but it might go like 5 minutes overboard. So when you do make your Colab, I want you to change the runtime to GPU. This is just so I can mount stuff onto the GPU on this. And yeah, the very first, so Colab has some Python packages already installed. That's nice, we don't have to do that. So that's one reason why we might use Colab. So I'm going to start off by just importing a couple packages. So we're going to import PyTorch, datasets thing, NumPy.
Wait, how did you get this screenshot?
How do I get Colab? Okay, so if you just
Right now it's like a text.
can
Darcy,
all right, no problem, no problem. We got people sitting here to help. Is everyone okay with like setting this up?
do
So
you want to increase this?
yeah, let me zoom in. All right, we're gonna import .nn .func as f. What else I want? Import torch.optim as optim, and we'll figure out what else we need afterwards. So the very first thing I'm gonna do, in this example, we're just going to try and make a very simple convolutional network that can train off MNIST data. Who here remembers what MNIST data is, or has like seen it? Cool, cool. Yeah, so just like sample data that is like publicly accessible, so you can train on basic stuff. So to get it, I'm going to call train equals data. Let me actually do this. Oh, and just so I know, who here has used Python before? Or is anyone just uncomfortable with it? Okay, well, it's Damani. You're gonna have to help her out, and him too. Alright. So yeah, just look on with your peers and they'll assist you. So torch equals data sets dot MNIST. Download equals true. I'm gonna say, so just so you guys can see what I'm doing right now, let me insert a cell block. So if you're ever confused about commands I'm doing, you can just type help, and then you can just like type in, you know, whatever the thing is, and it'll give you like the arguments or whatnot. So right now I have the root, which is going to be the root directory we're downloading the data to. It's going to be local to the actual Jupyter Notebook, so it'll be here in files. Download true just means we're downloading it. Train, this is going to be the train partition to data, and transform, I'm setting to none. Don't worry about that. Typically people use transforms when they're using this, but I think it's kind of magical, so I'm just not going to for this purpose. Test datasets.mnist data download equals true, train false, because this is not the train test set. All right, So when you run this block of code, it's going to run for a second because it's downloading stuff. So as it does that, for the sake of time, I'm just type in some other lines. So I'll explain what this is after it's made because I can't really show you data that's not there. Yeah, my fault. Let me zoom out. I think that, yeah. For x and y in train. Okay, actually I'll just do this. So now we have our data. Cool. So if I type in the length of train, for example, you'll notice that it outputs 60,000. So the MNIST dataset is basically 60,000 images of handwritten digits between 0 and 9. So if I show you guys what one of these images look like, I can just do train of 0. This will show you the actual image. It gets rendered inside of Jupyter Notebook. The actual type of this is going to be a pill image, I believe. Yeah, so Jupyter Notebook just automatically renders pill images. So this digit in itself was a 5. If I put in a 1 here, it's going to give me the classification, which should say 5. So it's digit 5 and has the label 5, right? So now I just want to basically I want to make our labels and our x's, right? And once again, we are going to be going over time, but if you guys need to go, you can just go. So np.array for x, y. So this is going to be the image, and this is the label in train. So I'm turning the image into a numpy array, and the only reason why I have this other, why I'm putting that array into another array is just because dimensionality inside of PyTorch. When you guys play PyTorch, you'll notice that dimensionality is kind of like a bitch. So getting that to work is like, yeah, a little annoying. So I already know this from experience. So now I'm just going to say label, comma, for label, for image label in train. I'm also going to get our test stuff. Yeah.
If you just do train.data, I believe, if you write that out.
Train.data.
Just print that.
Okay.
Yeah, it should give you the tensor of data.
Okay, so that gives us the x that I'm looking for, correct? All right. So I'll say train x equals train.data. Train y. Do they have the labels? Label? Okay.
Press tab.
Yeah. If it gives me an error, then I know it's not there.
Alright.
Labels.
Yeah,
It's not giving me. All right. It's not giving me it. I will just
Just dot tab.
train.tab.
It should give you the list. Yeah, there you go.
Okay. That wasn't. Oh.
Yeah, there you go.
So classes. Correct.
Yeah, so it should be targets. Yeah.
Okay. Cool.
Or, oops, just get rid of train.
Oh yeah. All right. So instead of really redundant thing I was about to do, this is better. So just so we know the shapes of this, or rather the length. Well, I can do size because it's tensor. So if you just do train x.shape.
What's the shortcut for the compile?
It's shift enter. Yeah. Yeah. Okay.
Is there a shortcut for the like adding another code section?
If you do shift enter at the last column, it's going to add a new code section. I'm going to just do the other thing because I want this format a little differently anyway. So, yeah. But tinker. So, okay, I'm going to undo this. This is going to take a second to run. Not the fastest thing, but just for sake of time. Yeah, this is basically just, before we had a 60,000 by 20 by 28, it's going to make it 60,000 by 1 by 20 by 28. So it's taking each image, putting it into an array, and putting that inside the main array. As you can see, there's a 1 here now, and this becomes flattened. So we're going to define a class. So class CNN. So NN we imported here. No, I did not import torch.nn as n. So PyTorch allows you to define classes to do specific stuff. To do stuff with the class, there's just 2 functions you need to have. You need to have the init and forward. So in it, I'm just going to do super CNN self. We're just going to call that, and I'm going to specify some layers. So self.convolutional layer is just going to equal nn.com2d 19. I don't know, 3. Let me actually label this so you guys know what this means.
In Python, you can get rid of CNN itself.
Nice. Yeah. Sorry. Stride equals 1, padding equals 1. So what this is doing is this is saying, okay, we have one channel. So the images we got here, if you remember, it was a train of x of 0. That's not going to give me what I want. Train of 0, 0. This is a grayscale image, meaning there's only one color. So there's no RGB, it's just like one number. So maybe just only R, whatever, right? So this is saying, okay, so there's one dimension in that axis. We want to use 9 different filters. Kernel size 3, so it's a 3x3 filter. Stride is 1, so we're moving it 1 by 1. And padding of 1, that way it doesn't shrink. And usually we would add more convolutional layers, but just to make it simple, I'm just going to straight up make this a dense layer. So I'm going to say dense equals nn.linear. This is a fully connected layer. So it's going to be the number of filters, or the depth of our activation layer, times the actual size. So the size is going to be 20 by 28 because I have padding, so it doesn't shrink. And the output, we're going to have 10 classifications because though it's 10 digits. Forward. So what we're going to do here is we're going to say, all right, in forward, A1 is going to equal f.relu. So f I imported up here. This just allows you to apply functions onto stuff. So we're going to apply relu to our conv network, which is going to take in our x, which is just the input. Next, I'm going to say, okay, so x is now going to be reformatted. So the dimensionality is going to be weird, so we're just going to squash it into a none by 9 times 20 times 28. That way I can feed into this linear network. And after that, I'm going to just return f.softmax of self.dense A1. So we're going to pass this squashed vector into the dense, and that's going to give us our output at the very end. So let's just run that. I forgot to run up here. Once again, shift enter to automatically compile. All right, cool. So now to see if this is functioning, I'm gonna just make the network an object. I'm gonna say, okay, cnn.forward of, let's say, train x of, I don't know, 0, 1. So I added this colon just because I want the dimensionality, once again, to be 1 by 1 by 20 by 28. So if I do this, a very last thing I was supposed to do was up here, we have to make sure this is of type torch float tensor, torch long tensor. Otherwise, it's going to yell at us for various operations. Let me just go down. Yeah, so as you will see, this gives us 10 numbers. So notice this exponent eats the negative. This is basically 0. So if I did something like, all right, I want to see what it actually predicted this number to be. So just so we know the label, I'm going to do print train of y of 0 and val. So I'm going to turn this into a numpy array, and then I'm going to apply np.argmax. So for you guys who might not know what np.argmax is, my bad, I have to detach this first. So detach just takes it off of, think of it as a, I spelled that wrong.
It's function call.
Say that again?
It's a function call. You have to put parentheses after detach.
Oh, my fault. Okay, so detach just takes it off of the CPU. So if I do argmax of something like 53523, np.argmax is just going to give me the index of the largest number, so 0. So you can think of it in our case of giving us a classification. So np.argmax of val is going to give us what it thought this was, and as we can see, the actual value was 5, because that's what it was in the train. Okay, so it's really bad, but we didn't train it yet, so that makes sense. So to start training, what we're going to do is we're going to say, all right, first let's just make a losses array. We're going to define a loss function. So I'll just say loss func equals nn dot cross entropy loss, and we'll make a optimization. So we're going to use Adam's optimization, if you guys remember from lecture. So optimizer equals optim. Optim, once again, I imported right here. Optim dot Adam, and this is going to take our CNN parameters. That's just saying those weights, and the learning rate is going to be 0.01. So for I in range of 10, so we're going to do this over 10 training iterations. We're going to say, okay, so very first thing is we have to get our output. So output is going to be our network, CNN, and we're going to just pass in train of X. All right, so after we get that, we're going to say our loss is now equal to loss func of whatever we got, and it's going to do the cross entropy loss. I could also do the squared sum mean error, yada yada, but I'm just using this one. Against train Y. Okay, we're going to get the gradients. I'm going to append the loss onto losses, and optimizer is then going to update everything based on those gradients. And if everything goes, oh, I spelled append wrong. There's 2 P's in append. Don't forget kitties, append spelled with 2 P's. I'm also going to just import matplotlib.pyplot as PLT. Cross entropy loss has no thing called backwards. That's because there's supposed to be the loss, yeah. I should probably mount this on the CUDA now. So just to speed this up, if you go back here, just add .CUDA to the actual train, and that was not where I was supposed to put that. Put it here. And if you add,
Puts in GPU memory.
yeah, so just loading everything to the GPU just to speed everything up. And I'm just gonna restart and rerun everything from top to bottom because everything's on the GPU. So when it's on the GPU, it's just gonna train faster. So that helps us. And yeah, this should be good. Does anyone have any questions? Because I went really fast.
Can you share this with us?
Yeah, okay. Yeah, so if you guys on the
Yeah, this
do I have the
same
slides?
thing is on.
On the slides, yeah, it's up there.
So the CNN completed.
Yep. And if I plot it, we get that. So as you can see, the loss was decreasing over time. So it's training. I should decrease the more iterations. I can show you guys examples of it, but yeah, I need to go. So thanks, guys.
Thank you.
Also, there's more Intel stuff if you want it.
Yeah. Does anyone want like the last bits of swag? Oh yeah. You want? Cool.
Yeah, I'll stuff through, so like you just get for free. Yeah.
What's up? My name is Fight.
Right.
Fight. I'm a physics major.
Cool.
That's my friend. We're actually taking a graduate class on machine learning.
542.
No, 895.
Oh, cool.
For its physics department at TRS.
Gotcha.
So I don't know. Like recently I've been drawn towards not going to graduate studies for physics, and I'm exploring a bit. So I am taking a data science class. I'm taking a machine learning class. I'm looking a bit around. So I was interested in participating in this. We're actually covering. Right now we just finished all gradient descent and
Nice, nice.
Adam, RMS prop.
Yeah, so.
And we're doing some we're doing display regression right now, and
Gotcha.
lasso technique and stuff like that. So I don't know. I was interested. We were interested. My friend had to pick up a call, but we were interested in joining and seeing a bit what you've done. I know you already started. It's like been 4 weeks.
It's fine. You can just like walk in. Like, yeah, no problem. Do you get one?
Yeah, I got it. Like, wait, is this like, what
It's
is-
swag left over from the machine learning conference we had.
Oh, I see,
So
I see,
yeah,
I see.
there's like gummy bears and like some goodies inside.
Oh, I see. But is it like an online learning, like free?
Uh,
I can learn about AI
Intel has stuff, so you can look at it. I guess I don't. Ask
Yeah,
Devin.
ask about like the Intel stuff. Like they have like Intel Academy.
Yeah. So
I
this.
don't know just how to join. I know you have a Slack group, like us.
Yeah.
I don't know if you use that to communicate actually.
So basically, before this is the first time we're having this as a class. Before it was just a club. We would host these workshops before we come in. So the reason why I made a class was because it would increase attention rates, and you get credit now for attending. So it was like dual purposes. Kate Sanko, the leader by Typeform of machine learning, basically in this campus, was basically encouraged us to do it like that. So as far as joining stuff, I would say ask that beauty over there sitting down, and he can add you. And yeah, we're glad to have you along. So we're never really going to go into like mathematical detail, like where's the derivation of like cross entropy and stuff like that. But it will be like very high level stuff, and we're just hoping people can be able to like start coding stuff.
No, that's actually perfect because we are doing all the mathematical
Yeah.
stuff right
So this is
now.
like very just high level. You know, we just breeze through a bunch of stuff. This lecture.
I want to be here more for like working, talking about it, like looking at what you're doing in general, just exploring a bit the field.
Yeah.
Just understand. So I have a Slack.
Yeah, we have a Slack, we have a Piazza, so just ask him and he'll give you the resources.
Okay. And
Last one.
Alright.
okay. And for the material, do you
The
post them on
material-
Piazza usually like the slides you use or stuff like that?
So we have a GitHub / view VUMIC. Yeah, so if you go to like this link, it'll have like the weeks, and then we'll be posting this workshop soon. But you can see all the previous lecture notes.
Is this CS200?
Huh? Yeah. So this is a 1 credit course. It's very light, as long as you kind of attend and then do one project. Then
We'll also have the slides on Piazza.
yeah, he's not signed up on. He's a walk-in. So
I just walked in.
Yeah, do you wanna sign up on Piazza?
no, you can take.
Good
Kinda
luck
skip,
today.
yeah. I had to rush the last part because the first half was 40 minutes.
Yeah, that took a while.
Alright, see you guys.
We do have a Slack, but it's not that big.
Yeah.
Like, we've kind of Piazza in place.
I just started using it today because I have a project.
That was pretty
Slack is so good for projects, not that much.
For like
Well, it's actually good. We just don't use it. Our classes don't